Okay, so for a source at rest, the speed of light is c independent of the motion of the observer. So that's like saying, suppose I have a flashlight here, this is at rest, it's a source of light which is shining a beam this way, and it would be telling me that the speed of light is independent of the motion of the observer. Okay, so suppose we've got this beam of light coming toward me, and I'm at rest with respect to that source, that flashlight. So how do I measure the speed of light? Well, what I do is I take a meter stick like this, I time how long it takes a light wavefront to cross from one end of the stick to the other end, I time how long it takes, and I divide, I get the speed of light. Okay? And I would find, 3 times 10 theta whatever. Now this is saying that I would get the same value for the speed of light even if I were running towards that light, which is completely bizarre. I mean, if light is a wave in ether, okay, it's moving at some speed, c, with respect to that still ether. If I now start moving with respect to that ether, moving toward that light, with a speed d, what speed should I measure? The speed of light. C plus d. If I'm running away from the flashlight, what speed am I going to measure? C minus v, right? So what if light instead is particles? Suppose we have particles coming out of this flashlight with some speed c, drifting through empty space. Okay, so if I'm at rest with respect to the flashlight, I see them whipping by me with a speed c. If I'm running toward those particles with a speed d, I'm going to measure. I'm running away. Okay, so it's totally bizarre, right? So this statement makes no sense. This statement is completely unbelievable. Okay, so just wanted to point that out. Okay, so this is totally bizarre. Keep your mind totally bizarre. Okay, so at the end of the day, what we're going to show is that T2 prime actually follows from this and the relativity principle. And the goal of special relativity was to try to understand, because this is in fact true. Okay, but it's not at all obvious how it could possibly be true. And the goal of special relativity is to understand why this is true. Okay, so that's what we're going to get to. All right, so in order to get there, we need Einstein's second principle, which is the more important principle, which is the relativity principle. Okay, so let's start over here. So we'll call this principle number 1. This is the more important of the two principles, and that's called the relativity principle. Okay, so I'll just write out a paragraph. I'll read it, and then we'll paraphrase it, and then we'll talk about it. Okay, so principle of relativity according to Einstein is that the laws by which the states of physical systems undergo change are not affected whether these changes of state be referred to one or the other of two systems of coordinates in uniform translatory motion. Okay, so let's paraphrase that to read this. Okay, then any two inertial observers in uniform relative motion both are equally entitled to consider themselves to be at rest. Okay? So, so let me just read the whole thing. So given any two inertial observers in uniform relative motion, both are equally entitled to consider themselves to be at rest. Okay, so the word inertial here, the word inertial means that the observers are not experiencing any acceleration. Okay, so they're floating through empty space, and they have their jetpacks or their rocket engines or whatever turned off. So they're not accelerating anyway. So this is not accelerating or rotating relative to the distance stars. Okay, that's a very deep statement there, but we won't actually fall into that black hole. Okay, so not accelerating or rotating. And they are in uniform relative motion. So what Einstein has in mind here is just two observers floating out in the middle of empty space, just drifting there, and in some state of motion. And when one looks at the other, they say, you're going, say, that way with a speed d. Or this one looks at that one and says, no, you're going that way with a speed d, minus d. Okay? So they're drifting apart or toward each other, whatever, some uniform relative motion. Both are equally entitled to consider themselves to be at rest. And at rest here is putting quotation marks, meaning the same sort of thing as at rest over here. Okay, so we're going to tie these two together with that word, with that phrase at rest. Okay, so let me give you an example of this. So suppose that you are in a train